thank you so much. First, I would like to thank the organizer for this very nice workshop where I feel we have exchanged a lot of ideas and motivation to continue exploring Carrollian holography. And today I decided to talk to you about some recent development I've made on asymptotically leaky boundaries. And what I'm going to tell you today, it's really based on a joint work with Bob McNees at Loyola University in Chicago, and also Mark Geller that was here last week. And so I'm going to mostly talk about this paper and this one, and hopefully I can already give you some glimpse about new results that hopefully will be out before the summer. So the outline of my talk will be some motivation to study stress boundaries, and then I'm going to discuss a renormalization prescription for this type of boundaries. Then I will illustrate this renormalization on the partial boundary gauge and also motivate why it would be interesting to study this gauge. And then I will hopefully have time to discuss a variational principle that I will explain in due time. So let's start with the motivation. So as a physicist, really my first motivation was kind of a physical motivation that leaky boundaries really describe open system. And in particular, I'm going to talk about gravity, but you can think about that for gauge symmetry or in general, how to describe open system. And for gravity, when you have a gauge symmetry, so everything is happening on the boundary when you try to discuss symmetries. And what is happening when you have leaks? And leaks is actually something that we really familiar, maybe without knowing it's actually leaks. Is, for example, when you consider sky and you have some gravitational wave escaping at infinity, your system is actually leaky, it's an open system. Now we'll have some consequences when you treat symmetries. For example, your charges are not conserved anymore, the famous boundary loss mass formula, you're losing mass, you're losing energy. So this kind of system. But more generally, you can see what is happening when you have even a time-like boundary and you have some radiation passing through. And then I can refer to the talk of Sabrina's when she was discussing radiation in ADS, and she was saying that she was advocating also for leaky boundary. And also you might just being, okay, I have a system with a boundary at finite distance, and I just don't know what is the boundary condition on my boundary. I know I have a boundary, and I don't know, there is an unspecified dynamics, unspecified chemical potential there, and just you still want to describe the information you have on the inside of this region. So it's this kind of really like an open system like you would imagine in condensed matter and everything, just saying like you have access to partial information. And I think treating the symmetry in that context will give us very interesting result, but that's more like a long-term perspective. But right now I'm going to focus on asymptotic boundaries, and because I was trained also a bit as a mathematical physicist, let me be a bit more precise about what I mean by leaky boundary. So I always assume that I have a Lagrangian and a Lagrangian density, so I can vary this Lagrangian density, and this Lagrangian depends on some field phi. And then you have, as you all know, the equation of motion, and then you have a symplectic potential in this term. And if you are familiar with gauge symmetry, you know that this quantity is going to be very important when you want to compute your charge associated to gauge symmetry. And what I'm going to say is that for me, leaky really means that this thing is not zero. That's what I mean by leaky. And let me give you an example to convince you that it's a very physical situation for sky and asymptotically flat spacetime. If you use the Ashtekar-Strobel symplectic form, symplectic potential, this is really the news times the shear. So if you want radiation, this is not zero. Because if you kill the shear, you don't have the news, and then you don't have radiation. This is not zero in general, and then you have a leaky system, as I was explaining here. So we're going to treat the system where theta is not zero on shell. Another example is like if you take time like infinity, for example, IDSC ADS, and then you compute the symplectic potential a la, for example, Scanderis, you have the stress tensor times the boundary metric. In ADS-CFT, they see that as the VEV and the source, but Sabrina was advocating in her talk, and also Romain, Adrien, and Geoffrey in the Lambda BMS paper, that you want to keep this thing varying on the solution space. You don't want to fix, you don't want to see it as a source. So basically, this thing is non-zero in general if you want to have dynamical sources, in the sense that they vary on the solution space. If you have an unspecified dynamic for your boundary source, as well, this thing is not going to be zero. But it's still Dirichlet in the sense that you're still varying only from the boundary metric. So you can still infer some property, but we're not going to ask that to be zero. We're not going to have conserved Hamiltonian. We're not going to have all of that. But we can still define charges. Yeah. It's still what? So Dirichlet in the sense that this variational principle will still be able to distinguish between two physical solutions. So if you have Schwarzschild and another one, you're going to still be able to differentiate the two, but it's going to be proportional to the boundary metric. It's not going to be proportional to delta TAB. So you don't impose delta GAB to be zero, but you can still use the variational principle to distinguish two solutions in the bulk. That's what you want to have a meaningful variational principle. So, but you can just imagine you have a boundary metric fluctuating, and then you write it like that, and you just want to everything depending on the boundary metric. And that you can see that as Dirichlet. Yes? So during my talk, I will be staying in classical. So I think that's a very interesting question to go beyond the classical regime, and to then, when we understood the classical symmetry analysis, to try to see what is happen for quantum. That for sure, that's the next question. But it's, yeah, as we'll see, we have still something to figure out classically. But yeah, in this case, Alfredo, I see you still, are you convinced that that should be there for asymptotically flat space-time? That is not zero? Yeah, but here I don't say it's Dirichlet, but just saying that in general, theta is not going to be zero, and that's what I want to, that's my definition of leaky, and that's what I'm going to use. I think, I don't know if it's sufficient for sure, but I don't know if it's necessary. Like, but that's the definition I'm going to take. Just theta different of zero. But even though you have theta is different of zero, you still have interesting. You still have an interesting fact is that if you compute the symplectic form, and then if you contract it with one symmetry of your action, so here I assume I have a symmetry of my action. You contract it with a symmetry of reaction, you will still have, if psi is a symmetry and on shell in a certain way, but I don't want to enter too much in the detail, you still have this property that your symplectic form is conserved. So even though you don't have theta equals zero on shell, you still be able to have a symplectic form that is zero, that is conserved. But then what it means is that you can still define, this means that omega f, it's the d of something. In this case, the object you're going to use to compute, to build the charges. So it's going to be a codimension 2 object, living at the corner, and then the integration of this quantity will be the charge, and that's how you obtain, for example, the Bondi mass. But so even though you have theta non-zero, you can still have something like that, because you have a symmetry, and then you can still build some codimension 2 quantity that's going to be the charge of your theory. Not going to be conserved, still going to be your charge of your theory. But what is the price to pay to kind of have leaks? in particular is that usually you're going to have, maybe not leaks, but if you have asymptotic boundaries, in general, what's going to arise is some divergences when you try to compute stuff. The on-shell action usually for asymptotic boundary is divergent, then the simplex potential, yes. So you can, that's depending which point of view you take. So you can see it's, because if they are related by the equation of motion, it's equivalent to see the fluxes or the charges, because du of the charges give you the fluxes. So you can trade one for the other. And depending which question you want to study, you can do both. But as you see, that's really the flux. So, and you compute the charge from this guy. So essentially, it's everything is, you know, I mean, it's one, yeah. I'm going to talk about it. Thank you. Yeah, and for if you want a non-completely on-shell, there is something when you can add the notor identities in all this definition, and I refer to the paper if you want more details about that, but I will exactly come to the ambiguity, and I'm going to play with them. Codimension 2, so sorry, maybe here. So that's codimension 0, so that's codimension 1. So if you are in, let me be in 4 dimensions, so that's 4 minus 1. And then this one, it's a variation on the solution space. So this one is still a 4 minus 1 form. And then this one is a 4 minus 2. So one thing that happens is that if you have a asymptotic boundary, you have divergences. And the other thing that, that if you allow leaks, and I think that's really like a feature of leaks, is that you have more symmetries. So this fact is that if you allow the boundary metric to vary, you will have more symmetry on your solution space. That was Sabrina's point, that she was like, if you're on radiation in EDS, you need to allow delta, the source to vary, and then you have more symmetry, except if you fix it, then you have less symmetry. BMS6, Federico Capone's talk, you also have, he was also doing leaky, and then he had more symmetry as well. In 3 dimension, people in the room have worked out a lot on that, about relaxing this thing and then having more symmetries as well. So it's a very natural thing, but here I just put everything together. And yes, so that's the motivation and a bit of definition of what is my setup. And then now I'm going to show you how I treat these divergences. Is it fine? I mean, if you don't fix something, I guess you have less constraints, so you have more symmetry. It's not necessary, but just in general, you would. I mean, you expect to have more, but I could imagine some very specific case when you don't. But yeah. 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 I don't know. Probably there is, but I never work with them. Okay. Let me talk about renormalization. So I was saying you have like divergences when you look at asymptotic boundaries. And in the past, people obviously have treated these divergences. So notably, Kostas Kendris and collaborator, when they look at ADS, they have written some boundary Lagrangian in a way that everything's going to become finite. And then if you use the prescription of Comper-Marolf, if you are familiar with that, is really they're using the boundary Lagrangian to see how to renormalize the symplectic potential. So it's really based on the boundary Lagrangian, but here, because I don't know exactly what I have on my boundary, I don't really right now want to specify anything about my boundary Lagrangian, I will propose to you a prescription that doesn't rely on this boundary Lagrangian, that just rely on the bulk Lagrangian. So, and to renormalize them, I'm going to use this ambiguity Glenn was mentioning, and I'm going to call theta run. It's going to be my theta from the action, and then there is this y, and then you can also add this thing. So let me explain. So you see that theta is defined as the variation of the Lagrangian equal the equation of motion plus d theta. But obviously you have an ambiguity. You can always shift theta by dy. The other thing, I'm just saying that we have the bulk equation of motion, but then you can also add any boundary Lagrangian that don't change the equation of motion, and that we still have the same bulk theory. So that is this guy here. Okay? So here it's really like you take L and you send L to L plus dl. And then the symplectic potential is transformed such a way. And so Comper-Marolf, they were saying, I take the boundary Lagrangian that renormalize my action, and then this y are precisely the symplectic potential coming from the boundary Lagrangian, and then it was working. But here, I don't want to say that I know anything about the L, because I have a leaky system. So let me show you what is my prescription, Bob's and my prescription. It's, so just for sake of notation, you put your boundary at r to infinity, and then the other coordinate, I don't know, you can think about in terms of boundary coordinate, and you have the time and the angles, and it's valid in any dimension, but let me be in 4, so it's easier on the blackboard. And the other important assumption of this prescription we're using, we assume we know the fall-off close to the boundary of the field phi you have. And I'm going to be precise about exactly what I want, but it's, in practice, you always know. You impose boundary condition, you know how your field behaves close to the boundary. So it's quite a natural assumption, but Comper-Marolf use no such like fall-off, but here we're going to assume we know how the field behaves close to the boundary. And we also assume that the fall-off are reasonable enough that we can integrate something. So there is some mathematical assumption, but in general, polynomial works well, logarithmic term works well. So, and then the prescription is going to be, I will choose my y, this component of y, AR, as minus dr over theta a plus smaller than finite term. So because I know the fall-off, I can compute this, I compute the component of theta a, which is u and the angle. That, you have the bulk Lagrangian, you can compute theta. For example, you take Einstein-Hilbert symplectic potential. Then you can compute the component u and capital A. And then I define my ambiguity to be just the integral over dr of this quantity. And just the leading part, I don't care, that's subleading. I don't want to know what is happening there. Okay? Yeah. Okay, so yes. So I just mean you have to tell me. So here I'm assuming that I have a foliation that goes, that when I take a foliation labeled by a coordinate r, that when I take r to infinity, I land on the boundary. And then I want to know, sorry, the behavior in r, maybe that's a better way. In r. Yeah, so there might be divergence, no problem. It's just that I need to renormalize my my symplectic potential, I need just to know the higher order, and then that's going to be subleading. And then, since the theta r run, it's going to give me something finite. So basically, this one is really like, let me write this equation and then we'll see how it goes. So this theta r, if I do this shift with this y, is going to be the usual theta plus dA y r a plus delta L. And then I have dr plus integral dr. I forgot. What did I? Sorry. So, and let me just write another line, and then I can try to explain. So here I take this equation and I look at the component of this equation. And then you have this one, which is, and hopefully I got the sign right. So this choice of prescription to define the symplectic potential, what it does is like, here is shifting by a corner term. So this is living at the corner. So there is a du and a d capital A in there. And then this one, you see that actually it's canceling the leading part of, oh, theta u, sorry, theta A. I'm used to. It's kind of canceling the corner part of the symplectic potential. So maybe I should make a picture. So let's say you have r to infinity here, and then a point here. So u is going along that, and here you have a two-sphere with xa. So to compute the charge, I'm interested in theta r. And then what I'm saying is that I'm shifting something in theta r, but here I'm killing the corner contribution of the symplectic potential, if you want. Very good, thank you. Very good, thank you. I assume that I have some behavior in R that I can integrate, which is like for Bondi, for example, that works wonders. So like for Pfefferman-Graham, no problem. For like, I mean, polynomial, you can integrate. So, and log probably, yeah, you can integrate as well. So it's just as soon as you can integrate once the function in R, it's fine, this method. Yeah, I'm putting a cutoff and then like I do this prescription and then, yes. Yeah. So what it does is that, okay, okay, let me finish, we can, so after that, if you then compute omega run, which is the delta of this term, delta of L disappeared. So theta run, the full form will just have a component in R plus order one term. It's not just notation. So this omega R run, that's the one I'm going to use to compute the charge. Now it just has a component in R. It doesn't have any more component in U and in A because I did this trick. Sorry, I saw a lot of phase puzzle. But here you like, this prescription allows me to put theta A just a full delta exact term plus subleading. Now when I take another delta, this one cancel. So basically it means that omega, I put all the information about my symplectic potential in the R component of my symplectic form. By doing that, now if I go back to d omega equals 0, now you have that this one is also valid for the theta run. And if you write it in component, oh, it's 0, sorry. Yeah, well, plus, yes. So it means that only subleading. So it means that there is, no, what did I do? It's 0, so I guess, yeah, it's going to be D of, anyway, it's going to be subleading. So you see that I have something now that is not depending on R at leading order. So when I take the limit of this thing, R to infinity is going to be 0. So now on my boundary, because I put everything back in the R coordinate, which I can because of this ambiguity, I have now that omega R run is finite. And this prescription, it's really like you follow, I mean, it's just you use that, and you have a finite omega run. And you didn't need to look at the variational principle. And that's very nice, because for example, for flat, I'm not sure we have a well-defined variational principle like on Sky Plus, with like we know exactly all the term when we have leaky boundary conditions. So there are some prescription when you fix the boundary metric, but like for leaky term, it's not clear. So here it's just like give you something finite, just looking at the bulk Lagrangian, which I like. So if you compute, yeah, and yes? So compare Marolf, for example, we checked for 3 dimension in the paper last year, we did in this method and in the compare Marolf thing, and it gives exactly the same answer. So, okay, so very good. That was one of my next comments, so thank you. So this procedure gives you a finite ambiguity. Because I integrate over R here, so I can always shift by a finite contribution here, right? I mean, there is still this one. I fix all the divergent pieces, but I can always shift it by a Y that is finite. Because here, when I define that, I mean, it's an integral of a dA when I do it, it's like up to a constant in R, right? So there is still a finite ambiguity in this procedure, meaning that my symplectic potential, I can still shift this guy by a dy, but y finite. Now, I will allow only finite contribution. And that's very natural. I mean, first of all, compare Marolf, they also have this finite ambiguity. Well, okay, we can. You can see it as adding compare Marolf, you can see it as adding a new boundary Lagrangian, and then you have another finite ambiguity. But like basically, this finite ambiguity, you need to know more to be able to fix it. So in the case of, if you have an Hamiltonian formalism and everything, you know which kind of finite ambiguity you need. You know this precise term. But here, because I have leaks and theta is non-zero, I don't know, but I want theta finite because I want to use theta to compute charges. So I want finite quantity, but I don't know fully. I have still an ambiguity in dy. I don't know how to say it. Yeah. Okay, that's so. I mean, the Varnish-Brown method. I think in certain cases, because it just relies on the neutral identities, is like unique once you start with that thing, but sometimes it doesn't give you what you physically expect. Because, for example, if you have some divergences, the procedure is rigid. So you need to, here, when you have some asymptotic boundary, it's good to have this ambiguity to renormalize. So, but all these different formulations to compute charge are related by dy, by ambiguity. So there is a work by Simone Speciali, Roberto Oliveri, and then later by Laurent and Daniele, when they really show you how to go from one to the other. So hopefully I'm going to have time to comment on that. There is a part that's going to be present in all charges, and there is a part that will be due to this ambiguity that we have. Because if you want, here it's just really a corner thing that you're playing with. But the part that is living here, interestingly living here, that's going to be common. For example, you're always going to get the mass, which is common to everything. Then you can have some Heisenberg living in the corner and some other thing, but then I want to discuss that later. So, but for any time you compute a charge, you have to give you a prescription and a finite, it's a choice. And you can decide whether, but so people, when they claim they have a unique prescription, they often mean that they have a Lagrangian and a specific boundary Lagrangian that is given to them, and then they can have a prescription. So, but at some point you make a choice. You have to choose this theta, and mathematically it's like you have a. I mean, this one doesn't matter, but you have this one always. You have to give me which one is the one you prefer. And there is a good motivation for one and another, but that's the when you have a closed system, then you have like more reason to choose one prescription over another, for sure. Yeah, sorry. Which are yeah, that's it's just that you work with like an infinite, I mean, a boundary that is located at an infinite distance, and then you just have to bring back to some finite quantity. So I think it just, yeah, I think it's. Yeah. Yeah. Yeah, for sure. Yeah. Yes. Okay, so that was very formal. So let me show you an example when this thing was useful. Then, yeah. You use what, sorry? Yeah. No, so I assume that I have a set of coordinates and the coordinates are like fixed. They don't, like symmetry don't act on my coordinate. I separate the two. I assume that the coordinate commute with the symmetries, the action of symmetries. Yeah, but in practice, I think for asymptotic symmetry, people have found stuff by using coordinates. And then for sure, like, the hope, I guess, would be to write it in the, for example, Ashtekar formalism, when it's like everything coordinate independent. But to find new thing, I would say that this approach, I mean, like Bondi was using a coordinate to start to find a super translation. So I think eventually I agree with you. We should have something that doesn't depend on coordinate. But so far, but let me. In practice, you define where is the boundary, so you introduce a normal. So you need to introduce some structure when you define a subsystem. And then I decide to put it in coordinate. Okay, so the example, sorry, Glenn, can I go over? We discuss a lot, so. So, this gauge. So, this gauge, what was okay, I can, maybe by interest of time, I'm not going to tell you why the full motivation on why we started to look at this gauge in 4 dimensions, but in 3 dimensions, by a lot of people in this room, we have been seeing more symmetry by relaxing boundary condition. And then the question was like, what is happening in 4 dimensions for asymptotic boundaries at some point? And I think this is a very interesting framework because you have radiation. And so that's a good way to try to understand what are these new symmetries and what are the physical content of this new symmetry we're finding by relaxing the boundary. That's why my motivation going into this partial boundary gauge. And let me tell you a bit more about this gauge. So the line element in boundary coordinate, we saw it 100 times, I think, during this conference. And then I assume my transverse metric to be this line element. And so this is completely unrestricted. So it depends on you, it depends on the angle. All the functions in this line depend on all the coordinate, the boundary coordinate, and this one, they depend on the bulk coordinate. So this V is depending on UR x A, and so on. And what is very nice with the boundary gauge is that if you give me this, I will get the radial dependence on V, beta, and U using the equation of motion. So I was like, okay, I just need conformal compactification. So I just assume that my metric gamma AB start by that, and then I just do a polynomial expansion. You can add logs here. We've been discussing also with logs. That will be for another project that I'm working with Mark. But for the moment, like, just take that, and then you can use the equation of motion. And equation of motion will tell you, will prescribe you what are like the fall off of your field. And just to, this equation is a partial differential equation in R first order. So you have just one constant free, and all this one we're going to be determined in terms of the gamma AB. This one is a second order. These colors. So you have these two, and you have, this one has the angular momentum here, and then these two don't depend on lambda. So right now I'm using any lambda, negative, positive, or null, but this one depends on lambda, and you see that then this curly V start with, there is a lambda here, so it's more divergent than the flat case, and then the boundary mass is here. So it defined in terms of the other one. I didn't want to write it down, but you're going to have it. Yeah, so this one in there is du of gamma 0 AB in there. It's because the metric is time dependent. This one has inside the Ricci of the celestial sphere, but I didn't want to write them down because, and I think, so you have all the radial expansion, so that's good for my prescription I was giving you, because now I can play with the one I gave you over there, and I have all the R dependence, and so I can just proceed. And I think very importantly, I just want to mention this first order, like there is more equation when you go lower. This one are starting, okay, this one are like radial evolution. This one started to have some U evolution. And the first term is this equation that is very important when we discuss lambda equals 0 and lambda not equal to 0, and that appears in the work of Romain, Adrien, and Geoffrey, is this equation. So it relates lambda times the shear, or that's notation symmetry traceless, to du of gamma AB0. So it basically relates how the boundary metric vary in time to the shear. So when lambda equal to 0, you just have that chi has to have its shear to be 0. But when lambda is non-zero, the shear is related to the shear of chi. So this is kind of a drastic difference between lambda equals 0 and lambda not equal to 0. So I think that also was based, what Sabrina was saying during her talk, is that if you have a shear if you want to have shear in lambda different of 0, you need to have a time-dependent metric on the boundary. And then you can continue, and you have other equation, and I don't want to spend too much time on that. And then let me just comment about something. So this is so basically here it's a partial, yeah. Okay. Yeah. Yeah, it's in the U. But yeah, that's why, yeah, okay. Yeah. So it's, either this one, and we can debate where the radiation, I think it's like people, I think Adrien, Geoffrey, and Romain will more argue that it's in there. You and Beatrice will argue that it's in the U0. But you need to have some freedom in the boundary metric. That's what yeah. Yeah, okay. Yeah, no, thank you. Yeah, it's an important thing. But yeah, that's fine. Yeah. But in it, you need a right-hand side. You choose it. Yes. Yeah. But so, yeah. So, yeah, but I agree, it's a very important point. So here it's a partial bond gauge because I use basically to write this line element, I put GRR, GRA to 0, so that's 3 conditions. And I didn't say anything on R, except it's conformally. It's conformal. But now you can add the last gauge fixing condition, and usually, for example, Newman-Unti will tell you beta equals 0. Bondi will tell you that the determinant of this metric has to be the one of the two spheres. And with Mark, we have showed that you can propose a new gauge fixing which has more charges. So there are large gauge diffeomorphism, and so in principle they have to be there, and they correspond to this you can choose between the one you want, kind of a differential Newman-Unti or differential Bondi-Sachs gauge. So to choose this one, we computed the charge and saw that only in this gauge, only these two leading ones will matter. So here you see that it's like R squared beta and not beta equals 0. So basically it means that it's beta. So if you take beta equals 0, it means beta 0 equals 0, and this one you see that the traces, so gamma 2, this notation, sorry, means the trace. It means that the trace of gamma 2, which is D, the trace of DAB in the more usual notation, has to be related to the shear square. But if you say that now what you want is like only R squared beta to be independent on R, you basically just impose that after here is fixed, that will be 0, but this one you keep it free. So it's a differential gauge fixing, but it's a gauge fixing, and I don't see why we couldn't have it. And then if you are attached to the Bondi-Sachs one, you can do also a differential Bondi-Sachs gauge. And I think this is in the same spirit that what Glenn and Cedric were doing when they started to allow beta 0, because then you just ask that dr beta equals 0. Here we're just asking that dr cube. Did I forget a cube? Very good. dr cube beta equals 0, and then you have like just a bit more freedom. And the freedom we have in these two gauge, so here clearly the subleading is going to be different, the traces are going to be rated a bit differently, but what is important message is that in this gauge fits partial Bondi gauge, sorry, you have gamma, the trace of gamma 1 is free and the trace of DAB is free. And then I want to make a comment why this thing can be useful. Yeah, so there is okay, first comment. If you do that, you have more symmetries. They look very much like Javier, Adrien, Romain super rotation subleading symmetry they have, so that will be interesting to connect. But I think on a pragmatic point of view, there is 2 pragmatic point of view, no, 3, okay. So first, this kind of formalism unify Newman-Unti and Bondi-Sachs. So in the literature, people were doing computation in Newman-Unti, Bondi-Sachs. Here, if you take our thing, then after you compute everything, and you can then later put gamma 1 or gamma 2 to the value they are in Bondi-Sachs or Newman-Unti, and you have the formula. So you can compare the two things. The interesting at the level of the symmetry, is that if you allow this kind of symmetry that move these two guys, one of the charge you have is going to be proportional to the volume of the two spheres. So you're measuring some boundary data in the charges. That can be useful when you want to do Carrollian physics, or I don't know, try to get access to that, or to study cosmological solutions that modify the volume of the two sphere. So that might be also interesting for that. And the last one is very pragmatic, is that we realized when writing this paper in January that the Kerr metric was, when you go for Boyer linkage coordinate to Bondi, you first land on something that people were calling generalized BMS, general Bondi coordinate, like Fletcher and Loon in 2003. But it was actually this gauge. We didn't know when we write it. And I think it's bad to call something generalized Bondi, will confuse everyone. And then Glenn, in his appendix of his paper, actually took this gauge and do the last part of the coordinate transformation to bring it into Bondi. You could, I mean, like, it's large gauge transformation, so you can bring it to Bondi, strictly Bondi speaking, that's possible. But it's an extra coordinate transformation. Sometimes coordinate transformations are very tricky. So my hope is that for more not as nice solution as Kerr, maybe some perturbation of Kerr, maybe computing stuff in this gauge will be easy because you spare yourself one coordinate transformation to kind of study this kind of thing. So maybe just on a practical point of view, relaxing the gauge might be useful to perform some coordinate transformation. And you can see what is, we checked in the papers that we compute all the charge in this thing with these new symmetries and stuff. And then you can put Kerr in there in the generalized Bondi, which is a bad name nowadays, but and then you get exactly the angular momentum of Kerr. You get the same physics, which, I mean, thanks God, because if not, it's a bit bizarre. So I think that's why I want to motivate this gauge we introduce. And I think the last part of it is like, my question is like, I want you to understand what are these new symmetries exactly? How they differ from like the supertranslation. There is something already in the level of the Einstein equation, is that supertranslation are associated to the mass. The mass has an evolution equation. These guys don't. These guys are completely, these traces are completely arbitrary of U and XA. So they have different beasts. They are not the same. And I'm not sure in 3D we could see the difference, maybe, but I think in 4D that's really where we could see really the difference, because mass is sourced by radiation. This one is sourced by nothing. And it's kinematical in a way. And I wanted to kind of understand better this thing. And so what we decided to do was to look at ADS. Because ADS, there is a good notion of a stress tensor and conservation of the stress tensor that gives you the flux balance law. Romain, Adrien, Geoffrey did it in Bondi coordinate. So I'm going to base a lot of the next on that with the generalization to this gauge of what they did. And then we can see what is happening. So that's going to be the last part of my talk, and that's what is going to be in the work in progress that's going to appear soon. Is it clear? Right. Okay. We're gonna get there. Sorry. So that's. Oh yeah. Okay. Well. I'm gonna use Daniel's trick, so I don't have to jump. And I leave you that so you can have the notation over there. So now let's go back to ADS. ADS, so you can use this gauge in ADS. Okay. So what we were doing, so first in the work in progress paper, we applied this prescription to this partial Bondi gauge from lambda equals 0, lambda non equal to 0 for any boundary metric you want. It works. The expressions are long, are ugly, and you can find them in the paper, but it works beautifully. So really, when you look at theta r, like this one, you really have something like that diverge for, especially for lambda in R cube, and you have really delta exact term, and it's very complicated. And then you have corner terms as well, and that is exactly the one that appears in theta u. So you really see how all this prescription works in practice for this very complicated computation. But it does work, and I didn't want to just show you big formula for the sake of showing you big formula. But what we found is that, interestingly, so we found after doing all of that, we found this theta R run. So now I'm in lambda different of 0. We find a delta A plus a corner term. So that's really the finite piece. No, I mean, this one can have R term. So all the divergence is in A. That's what it means. Then you have oh yeah, and now we also to write that, we also starting to make some, to write it in this form, we started to make some assumption because, so we show that it's finite and then we put some assumption to try to understand the physics inside the symplectic potential. That's the goal right now. Because the divergences, the prescription works wonders, and so now I wanted to use the finite part in this gauge to understand this new pair of symmetry we have, and that's why we started by a simplest case before going to the full one. So all the divergences are here. And then you can just say, that's a complicated expression of all this, the data that we have. But then you can say, whether this one's coming from a boundary Lagrangian. I mean, you know it has to be, and is there a covariant expression of this boundary Lagrangian? The answer is yes, and we found one, so that was, I think, a very nice result, is that this A is actually, oh dear, I don't want to get over time, but is actually one part of the boundary Lagrangian from the usual holographic renormalization, prescription by Skenderis and friends, where you have the Gibbon-Stocking term, the corner term on the boundary, and all these things on the boundary of ADS. That's already a covariant expression. But then, because all what we do, we're in Lorentzian, and we're looking really at the fact that we allow to have corner in our story, only the boundary term is not enough. You also need to look at what is happening on the corner. And then, so that gives you that kills our square term, our cube term, and then we needed to add a corner term. I can just, that's ancient constant with some number. So this term really live in the corner, so that is B, that is dB. L is, sorry, yeah, very good. So L now I'm taking -3 over L squared. Gamma is really the transverse to sphere. And then we also assume then, so you have the normal here, but then we also assume a foliation in U. And then we define the extrinsic curvature of the corner embedded in the boundary. And that will cure the R divergences term. And that, I think, is the first time that it appears. I mean, I have to check the literature, so it's paper in written. So if I forget a reference, please let me know. That will be great to know before we put the paper out. But that's very nice because it's holographic renormalization with corner term. And we know that maybe to connect with flat or other thing, it might be very important to know what is happening at the corner. And then we have term for the flat limit. So as in the paper of Romain, André, and Geoffrey, lambda BMS, they were starting with this term, computing everything in ADS, then use the diffeomorphisms to write the quantity d nu in Pfefferman-Gram in boundary coordinates. And then they needed to add some boundary Lagrangian to be able to take the flat limits. But the term it was great, but I think we made an epsilon improvement of it, because the term were like an expression on the solution space, and here we have a covariant expression on the point of view of the boundary. So by interest of time, I don't want to write it, but it depends on the extrinsic curvature. You have the Ricci of the boundary metric. You have this kind of combination. It's long, but it is done. So you have a covariant expression on the point of view of the boundary. So that's, I think, a first result that is very nice, and the detail will be in the paper. It's going to appear. And then Then here, first we did the computation, and we had a massive long symplectic potential, very complicated. And so the key was to try to find some quantity we know are great. And I got inspired by this paper to look at the stress tensor in boundary coordinates. And then it's actually give you this part. It's very nice. And then you can look at really that the traces appear really in this thing. So like this one has, for example, gamma 0, delta gamma 2 as a pair in there. And other stuff, and I don't want to go too much, but what is important about my message, about I think I start to understand what these new charges are, that is relating to the flux balance law, is that in this this TAB has the mass, lambda mass, which is in general, it's psi 2 for when you have a cosmological constant, for people who know. Here you have some radiation, and here you have the angular momentum. Anyway, so you have the mass, angular momentum, and some radiation in the sense you want to have. But then you can see that if you look at the wide identity of this guy, it's really the evolution equation for the Bondi mass loss formula, the evolution of the angular momentum. So this one is really carrying information about the flux balance law. But then this one, we see that the extra pair of things, they live at the corner, which makes sense. And that's why they don't have flux balance law, because they actually, if you look at the symplectic potential and the symplectic pair, they are symplectic pair on the corner. So they really it makes sense, they are dynamic, they are kinematical, because you can define them at any corner, they're gonna be what they are at that corner, but you're not gonna be able to prescribe the evolution. So I think that's the first hint, the first thing where this one really carries the flux balance law, and these ones carry the corner pairs, corner symplectic pair that measure, then we can discuss like the coordinate quantity you have chosen, because it's going to be related to, for example, the volume of the celestial sphere. But then in EDS, at least it was very clear to make this split, because we knew we wanted to have the stress tensor, and then it actually works, which is non-trivial to massage. But yeah, so I think right now we really see that there is new symplectic pair living at the corner, and that have a different status from the mass, which I think that's the message so far that's how I understand these new symmetries. And I think I'm gonna stop here, because so we have 2 minutes for discussion. Thank you. No, so I don't, right now it's like, in pure gravity, is completely a time-dependent function, but arbitrary. There is no evolution equation. The ancient equation, you solve them completely, gamma 1 is completely free. But then if you imagine you take Einstein-Hilbert plus stuff, you could imagine that stuff sourcing this gamma 1. So that's also another motivation if you want to study, I don't know, with matter, like with a scatter field, with what you could maybe source this guy, and then what I'm suspecting is this guy will go from here to here in the symplectic potential. And by the Alfredo's comment about this part is common, I think, to everything, any prescription of the charge. This part you see, it's a corner, is actually, you can remove it by a Y, finite wide ambiguity. My viewpoint on that is like, if you have more symmetry, you should keep them. But you can also be very, how you say, like conservator and just saying, no, that's the only matter since the radiative space-time. Here, I think it's going to measure something not radiative. So for dimension, it can be very interesting to study what they do. Yeah. Yes. We use this prescription to be able to compute the charge for the partial Bondi gauge. Yeah. So I'm sure they... Very good point. No, so... Yeah. Totally fair. I think when we started this thing, at some point we were just like, oh, there is more, we should get more. So one motivation for the gauge we use in 3 dimension is that in ADS in 3 dimension, you had a charge associated to vial that was measuring like actually gamma 0. And when we tried to do the computation in Bondi with Romain, we realized this charge was not there. And so that was the first motivation to relax the gauge in the 3D equivalent of this one to get the vial charge. But then we realized we had 2 pairs actually, and they were living in the corner, and so that story started. So clearly this gauge is not the most general. There is more. I mean, clearly like you can relax GRA, like in the Bondi gauge. You can add angular part, which is essentially giving you Ehresmann connection in the Carroll some angular component. You can do that and allow for the rotation of the Ehresmann connection. Yeah, but so far I agree. So far I want to understand this one before enlarging anything more, because I agree with you. We should understand really what is the physics in this one, and maybe they're going to be gonna help when we want to make the connection with the super rotation at spatial infinity, because it seems that they have new symmetries that were very useful to be able to compute stuff in the Hamiltonian. So maybe that will be one of the things that they will appear. But I agree with you. That's why I'm doing this, to try to really understand what they are, where they are coming from, and before going to any more enlargement, because this thing is like heavy computation behind, I must say. So I think we should understand the simplest case before like generalizing to much more. And also, just a last comment: this charge has the same time as the vial, have the same type as the vial charge. So also to understand the vial charge in 4 dimensions. I think in 3 there is an understanding by like work by Glenn, Romain, Luca, and Alessio Keiko, where they relate that to the vial anomaly of the boundary theory. But here in 4D, the anomaly, when there is no, I mean, there is not the same type of anomaly in 3D. So anyway, there is room to explore. So so it doesn't mean that there is no physics. In 3D, we saw there is some physics. In 4D, it's not clear yet, but that's why I think we should explore that. And also maybe in celestial understanding if they play any roles, probably not, because they are due to the fact that you relax the boundary metric, but you know, Sabrina seems to do celestial with fluctuating boundary metric right now, so maybe it's going to be interesting. We'll see. Thank you.